Hi, in this video I'm going to be talking about problem 6.46, which was number 15 on our chapter 6b homework. You have a 4.5 gram particle moving towards a stationary 8.8 gram particle at 3 meters per second. And in the question, only one part to it, what percentage of the original kinetic energy is convertible to internal energy? Okay, this is a question lots of people had, concept lots of people have had trouble with, and actually will be the first time that we've directly calculated the percentage convertible, even though that comes up in a lot of the problems. So I've set up a collision table already so that I can work this out and think of it in the same way as all the other ones. So we've got a 4.5 gram particle. That's this one. 4.5 grams. It's moving at 3 meters per second to the right. Doesn't really say directions, but it doesn't. We can just choose that one's going to the right. And then a stationary, slightly bigger particle, 8.8 grams, that is not moving. Okay, so there's going to be a collision. The one's going to come in from the side and hit, and it's going to go off. So let's fill in the table. We have 4.5 grams. If we're going to put this in SI units so that our energies come out in the right form, that's going to be 0.0045 kilograms and 0.0088 kilograms. And that is a total of, we go to the calculator, which is still there from a previous problem, and 0.0045 plus 0.0088. Sometimes I find that I can do that kind of thing in my head, and sometimes my head doesn't want to do it. 0.0133 is the total mass, and we know that's important. So the velocity is 3 and 0, which means that the momentum here is 0 because it's not moving. And this one is 0.0045 times 3, 0.0135. 0.0135. And probably should write our units here. Kilogram meters per second, joules. So the relative speed is 3 meters per second. And then the kinetic energy, this one's got 0 kinetic energy because it's not moving. The other one is 1/2 times 0.0045 times 3 squared, which is 0.0675 joules. And for the moment, I'm not rounding anything if I can avoid it, so that I can keep that precision for my final answer. You do need to round the final answer to match the significant figures of the input data. So there was 2 digits in this input data. So my answer is going to have 2 digits when we're done. Okay, so the question's about percentage convertible. What percentage of the original kinetic energy is convertible to internal energy? So the total is 0.0675, and we're trying to compare the convertible energy to that total. Okay, so the answer that we want is going to be percent convertible equals the amount of convertible, whatever that is, divided by the total. And the total is the 0.0675. So how much of that energy is convertible? The book has a formula for directly calculating the convertible kinetic energy, and I don't personally like it because I don't feel like it adds insight into what's going on. The thing that adds insight is thinking about how much is not convertible. The not convertible energy is the energy that's locked up in the center of mass, which has to keep doing what it was doing no matter what happens in the interaction. And in this interaction, because this particle is moving and this one is stationary, the momentum is going to the right. That means after the collision, momentum has to be going to the right. And regardless of whether it is elastic, inelastic, whatever, the center of mass is going to keep moving to the right. So whatever kinetic energy is associated with the center of mass has to remain as kinetic energy of the center of mass in order for the center of mass to keep moving. I feel like that adds more insight into it than the formula that is in the book about the convertible energy. So the non-convertible is the same as the kinetic energy of the center of mass. So the center of mass has its own velocity, which we could figure out. I'm going to use the kind of shortcut formula, which is what's the total momentum of the system squared divided by the total mass of the system, the total inertia. That also gives you the kinetic energy at the center of mass. So total momentum is 0.0135 squared, and on the bottom, 2 times the mass of the system, which is 0.0133. That gives us a not convertible kinetic energy of 0.00685. And I won't round any. I won't keep carrying more digits than that. So that's the total amount of energy that can't be converted into other forms because it's stuck as the center of mass moving. So whatever else there is must be convertible. Okay, so the total is 0.0675, and the not convertible is 0.00685. Okay, so let's see. We've got 0.0675 minus 0.00685. That's the amount that can be converted. So we've got 0.06065 is the convertible divided by the 0.0675. So the percent convertible is 0.06065 divided by 0.0675, and we get 89.9%, which within the precision of the data that we've got, we're going to round it to 90. So what percentage? And this is probably give it to us in a percent, so I can write 90. Ooh, problem. Something turned out wrong here. I'm not sure what happened actually. So I'm going to have to do some troubleshooting. So either I've made a mistake in my calculation, or I've had a fundamental error in the way I was thinking about the problem. So we're going to have to work backwards. Okay. So let me make this slightly bigger so I can see the whole thing at once. What percentage of the original kinetic energy is convertible? Okay. So to find the percent convertible, I need the total, and I need the amount that is convertible. So my fundamental idea was that I needed the convertible kinetic energy and the total. Okay, and I thought the convertible was 0.06065 joules, and the total was 0.0675. Okay, so I need to check those calculations. Okay, is the total really 0.0675? Let's go to the calculator. So to get the total, I need the 1/2 times the mass of the moving thing, 0.0045 times 3 squared. Are those the right numbers for the mass and for the velocity? 0.0045 and 3. Okay. I'm okay with that. That gives me 0.06075. I had a little typo right there. 0.06075, which is going to change that 0.06075. It's also going to change this other number, so let's fix that as well. So then, well, actually, it's not going to change the momentum. The momentum really is 0.0045 times 3, which is 0.0135. I think I got that one right. Yeah. And then that's the total momentum. So the total momentum squared divided by twice the total mass. Total momentum squared, 0.0135. 2 times 0.0133. Cool. 0.00685. Okay, so that's the not convertible. So then The convertible is the total minus 0.00685. Okay, so this needs to be changed to that 0.06075, which means the amount that's convertible is 0.0539. 0.0539. Okay, so then I will fix that 0.0539 divide, and I get 79.8%, 79.9%, which I'm going to round to 80. Let's see. Whew. All right, something else has gone wrong fundamentally. I'm going to pause and track it down and tell the whole story. Okay, well, I think I've tracked it down. At least I hope so. If it turns out that I have another fundamental error, I'm going to throw my hands up. You can see sometimes you have good days and bad days. So I've checked through a whole bunch of things, and I believe I have the right method. I don't have any reason to suspect my method, but I do have a reason to suspect one of my calculations. When I was doing the kinetic energy for the one particle that was moving, I wrote 3 cubed right there. So this 0.06075 is wrong. It's not. That's not really the right energy. So this whole thing, I've got several different mistakes in here that are going to have to be cleaned up. So let's see if we can track those through. And that's squared. All right, I'm going to start writing things in red so we can see which things I had to fix. So that kinetic energy is 0.02025. 0.02025 if you actually square the velocity instead of cubing it. Okay, that's going to cause the total kinetic energy to change. The total I just erased the wrong thing. All right, 0.02025 and 0.02025 for the total kinetic energy. The momentum, I actually had that right from the beginning. That one was 0.0135 and 0.0135. Okay, good. So the total kinetic energy that I need to be subtracting right here is 0.02. Oops, put that in red so we can see that I made the mistake there. 0.02025. All right, but I think my center of mass kinetic energy was still correct because I was using the total momentum, which I got right from the beginning. Total momentum was 0.0135. So 0.0135 squared divided by 2 times 0.01333 is 0.00685. Okay, that's cool. Now I need to subtract those. So 0.02025 minus 0.00685 is 0.0134. Okay. So this is 0.0134. So that's the difference between the total and the non-convertible. So this is the convertible kinetic energy. Write that again right there, 0.0134. And then the bottom of this fraction isn't 0.06, it's the actual total, which is 0.0225. Okay, now we're going to divide those and see what we get for the percentage. 0.0134 divided by 0.02025, and you get 66%. Okay, and that actually makes more sense. I had a doubt in the back of my mind when I first wrote down that 90 because that seemed really big. The reason I thought it seemed really big is because the objects have a big relative speed, which means there should be a lot of convertible kinetic energy or non-convertible kinetic energy. So to have 90% convertible didn't seem right. 66% seems a little more likely. Okay, let's try that out. 66, submit. There we go. And tracked it down. So you can see both how easy it is to make little mistakes that give you fundamentally different answers. And also, maybe I'm hopeful that this is helpful to you in like how you actually track down an issue. And while I did pause it at one point and kind of track it down offline, for the most part, what I was showing you was exactly what I actually did do. And it was just, I was afraid it was going to take way too long to discover what the error was after I made a mistake a second time. But that's what I did is I tracked back through up to the top and then noticed that that was cubed instead of squared. But just to review quickly, the fundamental idea is the convertible energy is whatever amount of the total isn't stuck with the center of mass, since the center of mass must keep doing what it was doing. And so we found the difference, then we divided to get the percentage. So 66% of the energy in this system is convertible. And I think it's a good thing to think about what situation would lead to a high percentage of convertible, and what situation leads to a low percentage of convertible. What do the particles need to be doing in order for the energy they have to be convertible? And what do they need to be doing in order for that energy that they have to not be convertible? Good thing to think about.